Hi guys, welcome to another Learn Electronics repair video. This repair job came in yesterday, and this is very similar to the work I was doing in the early 90s when I was working on industrial electronics repair. So what we would have then, there was maybe, I think it was about 8 or 9 of us working in the workshop, and we were getting PCBs brought in by the sales reps from industrial equipment. And we would just get a PCB like this and ask, can you fix it please? And that'd be it, you know, can you fix it? You've got this. It came off some bit of unknown machine, and that's what you have. It could have come off. I mean, I remember getting circuit boards that I knew came off overhead cranes. I occasionally went out on site. Another one was from a machine that was effectively was a company who made Formula 1 engines and developed and down in Coventry, and they were using a machine that effectively measured the cam on the camshaft, the size of the cams as it rotated, the angular rotation and size, and I had PCBs from that machine. So I have all sorts of things to fix. This one actually is a little bit more down to earth. It comes off a coffee machine. And Handy Andy from the phone shop brought this, and he'll bring me anything these days. He says, Mitch, can you check that out? Can you fix it? And as I said to him, first of all, I don't actually know if this is faulty or whether the problem is somewhere else on the coffee machine. We can assume, because I live in the south of Gran, Canaria, which is a major tourist area, this will come off kind of like a commercial coffee machine, the sort of thing you'd find in a coffee shop, a bar, hotel, something like that. This is not from your average coffee maker. Yeah, could have come from Starbucks. So here we go. Or even Costa. Yeah, Costa Lot coffee, that one. Yeah. Can we fix it? Well, this sort of repair is basically down to pure electronics. So given something like this, okay, I know what it came from, is a little bit helpful. But we have to just diagnose what's in front of us, yeah? We have to just look at what's in front of us and see if we can find anything wrong with it. If we can't find anything wrong with it, then we can assume the problem is on the equipment itself. So let's start looking at this one. I'll show you my process of doing this, and let's see what we can work out. The first thing I can see here is we have a lot of terminals, and these 4 are all connected together. And these are all marked L and then N, which is on its own. And I have to assume that this is live and neutral. This is where the power comes in. We have a lot of other things here, meaning not a lot to me, many of them. Pompa, Macina, that's like Spanish for machine. Motor, motor. Line in, could be anything, thermo, and IFD. So that's what we have. And we have a few more down here. Porte or porter. Fondi, well, doesn't mean a lot. Display, that means a bit more. Ingress, this is input. Ingressa, Spanish, input. Sonderfluso, okay. Sonderfluso. Water. Aqua. And that's about it. That's what we have. Looking at the major parts of this, I can see here a transformer. And this is marked, so we have primary, 230 volts, 1-5. Oh yeah, contacts here, pin 1 and pin 5. So this is where the 240 volts comes in. Okay. And then it's saying secondary, 12 volts, which will be on the other side of the transformer. So this is where the secondary is. They look almost like they're connected to this pad, but they're not. Certainly this one isn't. Yeah, they probably neither of them are. So we know now where the primary is, over here. So the first thing we can check is, do we have any shorts on the input? This is obviously where something's happened. It's flashed over. So whatever's connected to here has drawn a massive current. So do we have any shorts here, and is this connected to the primary of this transformer? Because we can assume it should be. So let's have a look. I'll get the meter and then let's start looking around this board. We have the ohm meter, so we're on ohms range. Okay, I don't have the bleeper on. So the first thing we want to look at is we can see the problem here. This we know is N, neutral, so this is live L. So do we have a short here? No, we don't. So the next thing I want to figure out is whether this is connecting to the transformer. I can see the transformer here. So primary 230 volt, secondary primary 230 volt, secondary 12 volt. Which is which? Well, there's all the mains like wiring coming along here. Yeah, you can see this goes back to here. So is this the primary? Well, it's reading 17 ohms. So what's the other winding reading? Oh yeah, it looks like the mains actually goes to here. What's this one reading? Yeah, 1.7k. So the primary will always have the highest resistance, and anyway now I can clearly see that connecting from here along all this lot goes to this one that says neutral. So therefore this one, which is live, the other end of the primary must go to live. So what have we got? Well, it doesn't go directly because I've got 57 ohms. So if you go in there, something's in between. You'd expect it to go directly live and neutral, yeah? So you can see it comes from here. Well, there's the live, that's the neutral. So that's the neutral. And this is live. And we have, oh yeah, we have, right, this VDR1, this is a voltage dependent resistor. So this will go across live and neutral. And what a VDR is there for is if there's any surge on the mains above a certain voltage, this conducts it away. If, for instance, we have something that's meant for 110 volts, and you connect it to 220, this will just explode, but it will short out the power and stop anything else being damaged. So that one, I'm pretty sure we can see, if I just find, yeah, this is one terminal of it, and that goes to neutral. I can see it goes to neutral. And the other end, I'm guessing, must go to live. 56 ohms again. Okay. Oh, that goes to here. And then this is live. So whatever is in between is the 56 ohms, which is this thing. Ah, this says PTC. This is a thermistor, positive temperature coefficient. So basically the idea of this is that it starts off with a certain resistance, and as you pass current through it, the resistance decreases. I always thought it was called the negative temperature coefficient. Anyway, that's what it does. So this will start at like 56 ohms to stop an inrush of power, and once the current's flowing, this will drop down to maybe just an ohm or thereabouts. I'm sure if we had a part number on it, we could look up the data sheet and find out. But it's not important. So we can see now that that is between the live and the transformer. So that circuit's okay. So now we'd expect to find a bridge rectifier. I can see a bridge rectifier here. So that's just, yeah, it's these 4 pins in a square here. So here's the secondary of our transformer. We know there's no short on it. It's reading 17 ohms with the resistance of the winding. Does it go to this bridge rectifier? No, it doesn't. Okay. Ah, oh well. There's 2 bridge rectifiers. So there's a bridge rectifier here and there's a bridge rectifier here. Yeah, and this one seems to have tracks that go under the transformer. So I'm assuming from these two AC we have the 17 ohms, yeah? And this is the output. So this output now has a capacitor and it goes into all this circuitry. So the question is there a short circuit in here somewhere? So we can go across this and we can see, what is it, 38 ohms? No, 38 kilo ohms, yeah, 40 odd kilo ohms. So there's no short circuit in here. We can be sure that powers this capacitor up, charge it up, which is a 35 volt capacitor. Okay. And then this will power all this circuitry. This one, 79M05. That is a 5 volt negative regulator. Okay. This will be the microprocessor or microcontroller. I'll have to just get the microscope and see what that is. Here's the microcontroller. So it's a PIC 18F. So that's a microcontroller that effectively is switching all the, well, it's controlling the display, it'll be switching all the outputs on and off. This is the brains of the device. It also goes down to these. Oh, these are a little bit interesting. So Porter and Fondy, you can see, are connected through some high value resistors. So this is 39k, 39k, 39k. It's about 100k in series. I mean, we could even measure it. Yeah, and the same here. Yeah, so I'm suspecting that these are inputs that are monitoring something, and that voltage then is being dropped down through a lot of high value resistors, 100k, and there'll no doubt be another resistor going to ground and giving a low voltage signal that goes into here. That's what that'll be. So these will be monitored by some inputs on here. I think I saw something similar on here as well over this side actually. Yeah, these are 150k, 150k, like 450k in series. So this will probably be monitoring some sort of high voltage and dropping it down to a low voltage so it can be measured. Just a gut feeling, yeah. This pick will not run from a negative supply. It will run from a positive supply, and we do have this 7905, which is a negative voltage regulator. I'm interested to see if this voltage regulator is anyway connected to this pick, because I might have an idea what's going on here. Let me just see. This will be the output, I would imagine, and that will be ground, I would imagine. Is this actually going anywhere to here? I'll put the bleeper on so we can hear. Well, that pin does. How about this pin? I mean, that might have been the ground pin. No, that one doesn't. But one pin does. I'd have to look up the pin out for this. But it may be actually that this effectively has the positive supply from the 12 volts coming to it. Yeah, from this bridge rectifier. The positive going to here somewhere. We can just check that. Let's see, does the positive from the bridge go to this chip? Yeah. Yeah, the positive goes to that chip. So what you probably have here is a positive supply going to this chip, and then the ground of this chip comes back via this minus 5 volt regulator, which effectively holds the negative end above the voltage of the bridge rectifier by 5 volts. I'll just see. Negative end of the bridge rectifier. Does that go to here? Yep, it does. So they're basically using the regulator in the negative supply lead, what we consider the ground lead from here. But the same effect is, if this sets to 5 volts and we've got 12 volts coming in, the voltage across this is going to be 7 volts. I don't know what the spec of these is, but I'm sure we could work it out. But I don't think that's really important to the repair of this. I think it's just interesting. So basically now we know that we have a 12 volt supply coming into this area, the brains of the unit, through this bridge rectifier, this capacitor, and this regulator is involved in that supply. But we have some more things on the board here. We have this one, we have 2 here, we have another bridge rectifier, but I don't see a capacitor by it, and we have a couple of relays, and we have this. So what is all this doing? Well, these two are mounted close to all these, and I suspect they're to do with the switching of these. So let's have a look to see if we can work it out. First of all, we need to know what these devices are, but they're marked TY, as is that one, and I don't think they're transistors. There's another TY. I think these are triacs. I'll just show you what a triac is, and then we'll have a look at them. A triac is a semiconductor device. It has 3 pins. And this is the symbol for a triac. Like so. That is a triac. Possibly with a circle around it. That's a triac. So terminals A1, A2, or sometimes M2, M1, which is either anode or main, anode 1, anode 2, or main 1, main 2, and this is the gate. And the way a triac is used is basically like this. So we have the triac, gate, this connected to one of your mains terminals, live or neutral, doesn't matter which, because it passes AC in both directions. Your load, whether it's a lamp, a motor, but it's basically a mains powered load, back to your main supply live. And the live and neutral could be the other way around. The gate here, if the gate is positive with respect to here, then it turns on. The thing about a triac is, once you put voltage on the gate, it will turn on. As soon as it's turned on, you can now take the voltage off the gate, and it will continue to stay turned on until the main current stops flowing. Yeah? So let's look how this works. This is your main supply, 210 volts, sorry, 240 volts, 110 volts, 120 volts. This is your main supply, plus and minus. The way the triac works is, we can switch it on, for example, just as the mains voltage passes 0, yeah? So this is plus minus, AC. We can switch it on at this point. At that point, we can detect this, and we can then turn the gate on. And then this will now conduct for the remainder of this cycle until the voltage comes back to 0, at which point the current stops conducting and the triac turns off again. Okay? We can now detect it's on 0 again, and we can turn it on again, and then it conducts the other half cycle. It doesn't care, plus or minus. If you do this, so you continually turn the gate on at this crossing point, you'll effectively never get, you know, like some equipment where you press a switch and you hear a click on your hi-fi system. You know, because the hi-fi system is picking up the interference on the mains, the clunk when you first switch things on. So if you switch them on at a 0 crossing point, you don't get that. There's no spike, no interference on the mains, because you switched it on at the point when there was no current flowing. So that's called 0 crossing. And that's one of the main things you do with a triac. The other thing you can do with a triac is you can switch it on at some point during the half cycle. So if, for example, you switch the gate on here, it would now only conduct for this part of the half cycle, yeah? And if you then switched it on again here, it would only conduct for this part. So you can see, averaging this out, you've got half the power. So if this goes to a light bulb, it would now be half brightness. If you switched on even later, it would be very dim. Yeah. If you switched it on earlier, it would be very bright. So moving the switch on point from here to here will alter the brightness. It's a dimmer, basically. It's a dimmer. And this is how light dimmers work, by the way. The ones for incandescent lights, not LEDs. So this is a kind of primitive pulse width modulation. But all you have to do is put a pulse to turn the gate on at the right time. You don't have to worry about it. It sorts itself out. It switches itself off when it crosses 0. And that's a triac. And that's what I think these devices are. So let's have a look now to see if we can find a datasheet. You can see the marking on the first one. This one. Oh, it's TY7. It's not the first one. It's just the first one that I'm looking at. So you can probably see in the top corner the logo ST. That's SGS Thomson. A very common manufacturer of integrated circuits. And we have T4, 3570 and some 6K DQD number. Then we have another one. T4 and a different number, 0570. 3570, 0570. And the 6KD, a different number. I think these two devices are the same, and I think T4 is the part number and this is a date code or something. So that's those two. We had another one somewhere, another TY. Yeah, this one here. Yeah, it has a different number, but I think if we can look at one of them, if we can find one of these TYs, and there's another one on the heatsink here, TY2, which I can't easily see the number. If we can find out what one of these TYs is, they're all the same, and I think they're all triacs. So let's see if we can find a data sheet for this. And first, let's try ST, which is the manufacturer, and T4, which I think is probably the part number. This is the device, and we have that type. So the gate is on the right, and then A1 and A2 is the AC terminals. 600 to 800 volts, 4 amp triac. That's what they are. So we can assume from this that all the devices marked TY are triacs. We know what they are. Can we test them? This is the question. Yes, we can test them, but we'd have to there's two ways. We could power the thing up and see what voltage was on the gate, and then from that work out if it should be switched on or off, and see if it is switched on or off. But because of what's happened to this here, we can assume somewhere there's a short circuit. So I think it's good enough to test to see if these are short without taking them off the board, and that's quite easy to do. So we can go to the first one. So this is the gate. We can go from the gate to one of the main terminals, and we'll probably see nothing. I'll put it on the diode mode actually, see if we can see anything. So from the gate, yeah, it reads open circuit. What's it read to the other terminal? It reads like a kind of like a Schottky diode junction. That's probably okay. Yeah, it reads both ways. Doesn't read to that one. So I'd say that is probably okay. And is the thing short? This is what I'm really interested in. No, it's not short. So I'll look at the other one. If this reads sort of like the same, we know it's probably... Yeah, oh, that reads a bit different. I mean, bearing in mind there could be other things connected to this, but the main thing I think is it short? No, it's not short. So have a look at these other ones. This is another TY. So this is a triac of some sort. Let's see if we can find the gate. Well, this I don't seem to be able to... Oh, here we go. From there to there. Yeah, so this is probably the gate. Does it read the other way? Yeah, it reads both ways. Yeah. It sort of reads like the second one. So these are the main terminals. Is it short? No, so that one's okay. And then there's the big one on the heatsink, the last one. So I just kind of like get this where we can see it. It's there. I could probably zoom this out a bit better, but it's there. There it is. So again, this looks like it's the gate, because these seem to be the main power terminals. Oh, this reads very low. That one reads suspiciously low to me. I think this one we probably need to remove it and have a look. So where does this go to? I'll get the overhead camera, we can see where it goes to, be a little bit easier. We can see it's a little bit clearer now, we can see the bigger picture, yeah, we can see the bigger picture. So this is where we appear to have a short from the gate to here. Let's just go to resistance range. It might just be a low resistance. Oh yeah, this is not a... don't think this is a short. We can, to be sure, we can take this out. And I've definitely seen a low resistance there. It's like the thermistor is connected across this. This little thermistor we had here. Is that where this is going to? No, it doesn't go to there. That's very strange. 56 ohms. 56 ohms. I think we've seen a short somewhere. We've just seen it through the thermistor. So we're going to have to remove that and have a look. You can see this one. Power comes to the neutral to one of the main terminals. And the other one goes to here, which is this first one. thermo. No, use the thermo, whatever thermo is. What do the other ones do out of interest? And what's this bridge rectifier for? Oh, there's 2 relays as well. I should imagine them. So what about these 2 out of interest? They probably powering whatever's connected to here. So they probably go to these terminals. We can have a look. Oh, that one goes to there and just there. Yeah, so this terminal is driven by this. So when you're switching the gate of this, you can send power down here basically, either on, off, or effectively like a dimmer, or you know, affect the speed of a motor or something similar to that. This says I thought it was Messina, but I've realised this isn't Spanish, although I'm in Spain. This is Italian, because if it was Spanish, it would be Canaria, which is like M-A-Q, U-E, and this is M-A-C-I, which in Italian is macchina, which is machine, anyway. Machine. So that goes to there. So the other one must go to one of the other ones of these. No. Actually, it doesn't go to one of those. Where does that go? Oh! See this track? Does that go to the bridge rectifier? Let's have a look. Yeah, okay. So that one goes to the bridge rectifier on this pin. Yeah. And then the output of the bridge rectifier, I'm guessing on the other 2, whichever's the positive or negative, is probably going to go back to one of these terminals. Seems to come up this way somewhere. Yeah, that one. Line in. So this is switching on and off, and the output is going through a bridge rectifier and powering up whatever's on that one. So that's what that's for. There's 2 relays in here, but I can't imagine there's a short circuit with the relays, and we already know there's a short circuit possible with this. So the relays, what are they? They're 12-volt relays, so they're going to be powered from over here. From this. This is going to control the relays, and they're going to switch something. Well, one of them goes to that bridge rectifier, so it's involved in switching whatever this must be acting kind of like a dimmer, yeah, effectively, and then the relay is actually switching the power. I can see that goes to the relay. The other one's not being involved in something similar to that. But anyway, that's a bit of a nosy around this, and I'm hoping you can see how I would go about diagnosing this sort of problem. And the fact is, the only thing I can really see wrong is something here. There's a couple of diodes down here we can just have a quick check out of interest. Diode mode. A couple of diodes, or that reads like a good diode. There's also some transistors around them, so it's hard to say, but neither of them read short, and we've definitely got a short somewhere. So I'm going to have to say that this is the thing we need to look at. We worked that out 10 minutes ago, but I thought you'd be interested just to have a look around the rest of this, how you would go around working on a board like this. Okay, let's look at that. I've taken the clip off that held this to the heatsink, so we can now just desolder this. 3 pins. I'll add a little bit of a leaded solder first. This just makes it easier to do. So a bit of leaded solder, a bit of flux, 3 pins. Okay, we can soldering iron's ready, I think. Yeah, bleep. Nice with these T12 soldering irons, they warm up really fast. So a bit of leaded solder in there just to make it easier, and then we'll use the vacuum desolder just to take this off here, because it's just the easiest way. These things were invaluable, by the way. Yeah, you can do jobs without it, some of them, not all of them. But you haven't got to fix many things to pay for that, yeah. Right, so there is the triac. Let's see if this is actually any good. We can use a little component analyzer. I'll try this, and I'll try the little one that I bought as well, the €5 one, see if that will also do it. This is the Peak Atlas, is a very nice bit of kit, but there are cheaper devices around. I wouldn't say they were better, but they're cheaper. But they might be just as good. Let's have a look. It's covered in pigeon shit, but I don't have pigeon shit on my fingers. Horrible stuff. I think I'll wipe it off. So let's see what it says. Yeah, it says it's a faulty component, okay. I can show you what a track would normally test like, but this is saying it's duff. So that is the problem with this. Let me just show you a good triac as well, just to prove the point. This is a good triac. We can try it. We can try the triac, yes. Connect this up. 2, 3. A sensitive or low power triac, okay. That's nice. Let's have a look at what the €5 component analyzer thinks of all this. So that's what I have. I love that. I can highly recommend this. Formally recommend this. This is probably what you've got. It's a lot cheaper. But no, maybe some of you guys don't just buy things because it's the cheapest. Okay. Let's start the tester. What's he think of my triac? It's a triac. Yeah, it knows it's a triac. Let's see what it thinks of the dead one. And I'm going to get this pigeon off this. It's horrible stuff. Actually, I must stop saying that word because YouTube won't like it. They say it's not advertiser friendly. Okay. Okay, it's 2 resistors. So we know that the £5 component analyzer is just as good in this case as the £60 one, yeah. So here's a good triac. I actually bought a whole pack of these at one point from somewhere because they're just good, common, you know, useful triacs. Basically, I've got some smaller ones as well. So hopefully we can actually use this to fix this. We need to find a data sheet, so let's have a look to see what this actually is. Here is the triac BT139600, which I think is a 600 volt triac, and this is the one that has a short circuit that I removed from the board. So this one is another ST, and it's a part number. Let's get the torch and let's have a look if we can read it to see what this thing is. Not easy to read. I'll look down the microscope and see if I can actually see better than you guys can see. So it's ST BTB16 700 BW. BTB16 700 BW. So let's look at these 2 data sheets and see if we can use this one, which I have a whole box full, to replace this one, which is faulty. I will just test that the T2 or A2, M2, it's called various things, is connected to the tab, which it is, which is the same as the one that we took out according to the datasheet. And in fact, according to what I can read. So we can use this in this device. I've put some of the previously mentioned nasty white stuff on there. I've put the clip on to hold it in place. We'll just solder this in. And then let's have a think about this repair. Here we go. Just trim the pins off this. Our PCB is repaired. So I hope you can see, even with no information apart from data sheets and our own knowledge of electronics, and I'm sure everybody's watching this, if you've been watching the channel for a while, your knowledge of electronics is improving, as is mine, just by making these videos. And yet, even with practically no information, we found a fault. And it was a short circuit in a major power device, which is a very good reason to explain this. But I'm not sure it explains all the story. And this is why. This end of the triac is connecting to the neutral. This is the gate where we saw the low resistance before, and we can just check that again now. Yeah, it's high now. That's on diode mode and resistance mode. But we know what they look like in diode mode. Yeah, it's high. It's not 56 anymore. So the triac's good. This goes to neutral. Then the other main terminal goes down to this terminal. And this terminal says thermo, which even in Italian, I can tell now it means heat. Yeah, so this is probably the heater that heats up the hot water in the coffee maker. As a guess, I don't have the coffee maker. And the other end of the thermo will no doubt come back down to here. So even if this was short circuit, the most likely thing to happen is that the heater will come on and you can't switch it off until you take the power off. That it just boils, yeah, and you can't switch it off. It wouldn't explain, in my opinion, why this happened. The only thing that explains why this happened is because the thermo went short circuit heating element. So when this turns on, not only did it blow this, but it also blew the triac that was supplying the power to it. So there we have it. I'll give this back to Handy Andy. I will tell him that before he fits this, he needs to test from here to here, once it's reconnected with a multimeter, does he have a short circuit when the thing is plugged on here. If he has a short circuit, then he has a short circuit heating element, which he needs to be replacing first. If he doesn't see a short there, I will also just suggest that he checks from here to safety ground. Has he got short to ground, or so effectively like the heater's shorted to ground, or it's cracked and it's going through the water maybe. But I think that's less likely to do that. If it was a short to ground, I think all that's going to happen really is that the earth leak is triple below. Yeah. But you know, I think these things are just always worth, if you can't find a short, then just check that one just to be sure. And if he does see a short, don't plug this and switch it on, because you're just going to blow the triac up again. There we have it, guys. You can see we can take a PCB from a device that we don't know a great deal about, and just using pure electronics knowledge, we can repair it. And in many cases, the repairs will be this type of thing, short circuit power devices and such like. I know repairing a coffee machine isn't the most glamorous sort of work out there, and I know that a lot of you guys just want to learn to repair GPUs, and I get it, I get that, but I would have to say to you this: if that's your approach and you want to learn electronics repair, you want to make money from electronics repair, you're narrowing your options a bit too much. Industrial and commercial electronic repair is a very, very good way to make good money, and easier than fixing GPUs. Okay? Something like this. The machine is probably $1,000, more or less, possibly quite a bit more than that. And to replace that machine is a major commitment. To get a service engineer from the Italian company, if you can, to replace it is a major commitment. If they send you a PCB, that's probably $500 to send you that to replace it yourself. Okay? As you see, $1 worth of bits, less, so many cents worth of bits, application of electronics knowledge, pure electronics, and it's diagnosed. We know now either A, this will work, or B, we have a short circuit load on here, which is almost certainly the heater. If we have a short circuit heater, we can then get the model number and get a heater. That's fine. You can easily charge these jobs out at like $100, yeah, for this sort of equipment, because it's worth it to the customer to repair it. And also, quite likely, you can repair it very quickly. If this solved the problem, job done, yeah, things working again today, they're back making money. If it needs a heater, we know we can get a heater, they're back making money. If you want to get into this, if you want to get into this area of work as self-employed, I would suggest you start by trying to find companies local to you who sell this type of commercial catering equipment or other forms of industrial or hostelry related equipment, things used in pubs and restaurants and hotels and such like, and any other sort of automation and mechanics. Go to some of them companies and say, look, I can fix your PCBs quicker and cheaper than you can get replacements, because you can pretty much guarantee those companies will be just acting as an agent and buying in the parts and fitting them. And if you can pick up some work that way, if you got any PCBs, offer to repair them. Yeah, maybe make them offer. Look, tell you what, give me one or two and see if I can fix them for free. If I can fix them for free, let's talk about it. Yeah, that sort of work is available anywhere in the world, in any sort of economic situation that you might be in, because there will be businesses in industries and in such as tourism or in catering or in hostelry, in entertainment. There will be venues who have money for sure anywhere. Okay guys, so a little deep, but that's from Uncle Richard, yeah? From Uncle Richard. Think about it. It's a good way to make some good money. Okay, see you all soon on another Learn Electronics Repair video. Ciao for now, guys.